Jean-Michel Friedt has expertise in the development of passive wireless acoustic transducers acting as sensors with the Sensor Company and the Time and Frequency Department of the FEMTO-ST Institute in France. He's focused on bulk and surface acoustic transducers and the associated radar-like electronic systems for the development of passive sensors interrogated through wireless radio frequency links. He's currently an associate professor employed by the Université de Franche-Comté in Beslan, France, located at the Time and Frequency Department of FEMTO-ST for his research activities. Following the 3-month visit to PRM Sato's laboratory in CNEAS in Sendai, Japan, at the end of 2017, his activities have shifted toward passive radar and phased antenna array processing, still applied to passive acoustic sensor cooperative targets. Please welcome Jean-Michel Friedt.
The presentation we're about to stream here is about software-defined radio-based synthetic aperture radar, noise, and OFDM, basically Wi-Fi emitter radar mapping. This is a work that we perform with my colleague Wei Feng, and it aims at completing the presentation we make at the Software-Defined Radio Academy last summer. One of the focus is how to best use the various frameworks we have access to. So basically GNU Radio, of course, for radio frequency signal processing, Python, which is the underlying language of GNU Radio, and Octave, free open source implementation of MATLAB for signal processing. So what was the outline of the talk? During lockdown, we were stuck at home and wondering how far this house opposite of our balcony was, and we wanted to make a radar system to measure this range. So the French Geographic Institute aerial map says that it's about 50 meters. So basically, we would like to use readily available hardware for fabricating short-range radar system able to map the distance to the house about 50 meters away. So basically, what do we have? We have DVB-T antennas or Wi-Fi antennas. We have PlutoSDR and Ettus Research B210 and various passive radio frequency components, splitter attenuators. So what we would like to try is to assemble a radar system for mapping various targets, and at the end of the talk, we'll show how to make interferometric synthetic aperture radar, so sub-wavelength range measurement. What is the basics of radar systems? Radar systems are based on a fundamental physical property, which is the range resolution is the velocity of light divided by twice the bandwidth of a signal. You see here that the carrier frequency doesn't appear, only the bandwidth, and the twice here is the two-way trip from the emitter to the receiver. So the objective of a range resolved radar system is to increase as much as possible B to have as high as possible a range resolution. So increasing B could be a frequency swept radar, which is the classical approach of a chirp. It could be OFDM, orthogonal frequency multiplexing, as used in Wi-Fi. This is the approach that was discussed in Martin Brown's PhD. Or what I like is noise radar, where you modulate the carrier with a pseudo-random sequence, and by doing this, you spread the spectrum over the whole bandwidth of the rate at which the property, either amplitude or phase in our case, will be varying. This is the approach that's used in the CDMA modulation of GPS, and actually it's been known for a very long time. If you look at some of the oldest literature on noise radar, 1957, it was already well known that you could spread the spectrum using a white noise. And why does spread the spectrum allow for range resolution? Because the correlation between a reference signal and a surveillance signal will show a peak at the various delays introduced by the targets. Now, correlations by using the convolution theorem are best computed using Fourier transform, because the Fourier transform of a cross correlation is the Fourier transform of a reference signal times the complex conjugate of the Fourier transform of the surveillance signal complex conjugate, because you have to flip time with respect to the convolution. And another way of doing this is using the Fourier transform of reference, but instead of flipping time by using the complex conjugate, you can take the division. This will allow for removing the amplitude variation within the spectrum, and yet the phase will be inverted by using the ratio, the inverse of a complex quantity. Now, there's a challenge here in GNU Radio being synchronizing the emitter and the receiver is a challenging task in GNU Radio. So what we're doing here is, instead of trying to synchronize emitter and receiver, we have one emitter, in our case, the PlutoSDR, and this local oscillator will modulate, will generate a transmitted signal, which is modulated. And what we're going to do with a B210 dual channel receiver is we're going to record, on the one hand, what is transmitted through attenuators to protect the input here, and use the received signal. And by having these two information which are both clocked on the same local oscillator, so we have two IQ streams which are coherent, then we can use GNU Radio to cross-correlate the stream. And because these two data sets have been collected simultaneously, we know that they are synchronous, so we don't have the issue of synchronizing emitter and receiver. How do you actually implement this? Well, let's first try to see how we can spread the spectrum. And for spectrum spreading, what we're doing here is we're using a random source, and this random source, which is DC block, just to remove the DC offset from the random source, modulates the phase so that we have a constant amplitude signal. And by modulating the phase, we spread the spectrum. As you can see here, this is the PlutoSDR output, which has been spread, and we measure using the B210 inputs on the Qt graphical user interface, frequency, spectrum, display, and what you see here is the background noise. And when you modulate your output here at 2.7 megasample per second, which is limited by the communication bandwidth with the PlutoSDR, you see here that you have this nicely flat spectrum over the whole bandwidth. So this demonstrates that we can have the spectrum spreading property using a pseudo-random sequence on modulating the phase of the output signal. Now, the challenge here is to collect the two signals and stream them to the processing circuit, and doing this while sweeping the local oscillator. Why do we need to sweep the local oscillator? Because, as mentioned, the communication bandwidth with the PlutoSDR is limited to about 2 megahertz, and 2.7 megahertz, if you take C over 2B, is 56 meter range resolution. And if you want to map a house which is located 50 meters away, that's not enough. So what you will do is to step the local oscillators over the frequency range and accumulate the various spectra at varying local oscillator frequencies with a constant B, the bandwidth. And the sequential sweep will allow you to stack frequencies. I learned recently that this is called frequency stacking. And so what we do here is collect time series, switch the local oscillator of the emitter and the receiver, and repeat this over the full accumulated bandwidth. Now, GNU Radio does not know how to change the local oscillator from the GNU Radio Companion flowchart. So what we're going to do here is we're going to program the local oscillator of transmitter and receiver using an external software, in my case, GNU Octave, because it's the software I know best. You can also do this in Python. And what we're going to do is stream the data continuously using a UDP-like 0MQ publish sync. And these data will be collected by Octave whenever they're ready. So what we have here is a constant stream, as GNU Radio wants us to do. And what we're going to do is only collect the data when the local oscillators have stabilized. So how do you actually implement this? This is the kind of Python code that was generated by GNU Radio. So you see here that you've got all your parameters. So for example, set the frequency, your local oscillator frequency for the PlutoSDR and for the USRP for the B210. And if we call this set f with a new parameter f here, then we can sweep the local oscillators. On the Octave side, we have a connection to the 0MQ socket, which is streaming the data from GNU Radio to Octave. And we have a TCP/IP socket where we can send information to the server here in order to change the frequencies. The socket is over here. So, for example, we send a plus symbol to tell the Python server to sweep the local oscillator, and at the end we quit the local oscillator. So this is what we described in SDRA. And since then, we've been told that rather than changing the Python code, which means that you have no longer the ability to come back to GNU Radio Companion to graphically change your flowchart, we've been informed on the GNU Radio mailing list, discussion mailing list, that actually you can use a Python snippet to launch your server, and you can include the server as a Python module. So here in this example, we create our server as a Python module, and this Python module is called from the Python snippet here, where we start a separate thread. And this separate thread is given as an argument self, which means that we're sending as an argument to the server all the structures that were created in this flowchart. And for example, here you can call this set F, so set local frequency or set F carrier frequency, and this allows you to change the properties of the variables in this flowchart. So in this example, you see, for example, that I change the local oscillator of my signal source, and indeed you see on the graphical frequency sync that the frequency, local oscillator frequency, has risen 4 times. So indeed it's working. And in the X term where we launch GNU Radio Companion, we indeed see the information that the local oscillator was changed whenever we send a command. So this is how we're going to work. We have a TCP/IP server running as a Python module inside the flowchart, and Octave will send information. In this case, it was a telnet, but we're going to run the socket from Octave, and Octave will, on the one hand, tell the local oscillator to sweep, and on the other hand, will fetch the 0MQ stream to display the cross correlation. So that's the resulting setup of the B210 with its reference channel through 2 attenuators to protect the input, the coupler, 10 dB coupler here, so that the output of the PlutoSDR is on the one hand sent to the transmitter antenna, and the receiver antenna goes to the second input of the B210. All the data are streamed through USB 3. And when we try to work with this setup where the local oscillator here offset with a B210 local oscillator will be cancelled, because these 2 channels are referenced to the same local oscillator. As we were collecting this data, we noticed that we had loss of coherence when we were changing the local oscillator, and that was tracked back to the fact that the PlutoSDR requires, with the default GRIO library, about 1 second to settle, because all parameters of the AD9363 here are changed whenever we change the local oscillator properties. We'll come to this later by updating the GRIO to only change the local oscillator, and this 1 second settling time will be removed. So you run this, so you sweep your frequency, and here is a noise radar centered on 2.4 gigahertz. We'll skip the VHF DVB-T experiment and immediately go to the Wi-Fi band, ISM band around 2.4 gigahertz, because that's what we're going to use later with Wi-Fi. And here what you see is if you correlate the reference signal with the measurement signal when sweeping this whole frequency band on the noise radar, so that's about 100 sweep plus or minus 50 megahertz, each collected with 1 megahertz bandwidth, you see that we have multiple echoes. Of course, you've got the direct crosstalk between emitter and receiver at 0 delay. But then we have a few echoes, which is already C over 2B. So this is already the velocity of light divided by twice the delay. So it's already a range. And we have echoes around 28, 46, 49, 54 meters. So this makes sense because the house is claimed to be around 50 meters away. And if you draw these echoes as circles centered on the emitter, this is my balcony here, you see here, this is the 29 meters, that's 46, 49, 54 meters. So these are the various ranges. And you see indeed that there are some structure that might match, obviously, all these guys here around the house that we want to map. But there is no certainty whether this echo here is the chimney, or if it's a house, or if it's one of these corners over here. So we do not have any azimuth resolution, we only have range resolution doing this. So now we would like to hide our emission in the surrounding noise, in the electromagnetic smog that we have around us. So instead of doing noise radar, you might also consider Wi-Fi, so OFDM, orthogonal frequency division multiple subcarrier access. And in the case of Wi-Fi, we have in Western Europe, we have 11 channels, each separated by 5 megahertz, so that's a bit less bandwidth, 55 megahertz, but we can do exactly the same. We can sweep the various carriers by emitting, by streaming information from this time the Wi-Fi dongle instead of the PlutoSDR. And again, you have the same story by cross-correlating the transmitted signal with the received signal. We have the zero delay echo, and we've got all these echoes here between 30 and 50 meters, so that's consistent with the noise radar measurement. The only trick here is that if you look at the spectrum, the OFDM spectrum of a Wi-Fi signal, then you've got all these sub-carriers, and because you've got this structure on the spectrum, you cannot use the complex conjugate multiplication for calculating correlation, because doing this will introduce a lot of side lobes due to these artifacts, and by taking the ratio of the measurement to the reference channel, you can cancel these magnitude fluctuations. And furthermore, because the zero channel is not used, it's wise to offset the receiver local oscillator with respect to the transmitter local oscillator, so that the center frequency is on one of these half spectrum. So in our case, we're sampling 6 megahertz and we switch by 3 megahertz the local oscillator, so that we can only collect the data away from this unused channel and avoid this hole in the spectrum. So this is all very nice. We have range resolution, but now we would like to have azimuth resolution to make sure that we know what is the target. So how do you add azimuth resolution? This is where the carrier frequency comes in play, not only the bandwidth. Now, what we know is that the beam width of an antenna is given by the wavelength divided by the antenna diameter. So how do you make a directional beam? Well, you need a large antenna. So for example, on this airport radar, you see that you have a wide parabola, which makes a narrow beam and allows you to know where the plane reflecting the echo are located in azimuth. Now, this is one way of doing it. Of course, I cannot put such a wide antenna on my balcony. So another way of doing this is to say we synthesize this antenna by moving the unique antenna, so the small antenna, broadband antenna here, over a range of diameter d, and this will allow us to synthesize such a broad antenna. So that's the basics of synthetic aperture radar, where you simulate an antenna with width d by moving the unique antenna with small steps. Here the graduation are every quarter wavelength, and so you end up with a 3 dB beam width, which is given by 0.89 the wavelength divided by n times the number of steps times the distance between steps. And for example, in our case, if we make something like 1.4 meter long motion of this antenna, then we have about 4.5 degree beam width, which at 100 meters gives us an azimuth resolution of 8 meters. So this will clearly allow us to identify whether the reflector is from the house or any other target. So by doing this, what you end up is having an antenna with a uniform spacing between antennas, and this will act as a uniform linear array where your plane wave is reaching your antenna with a wave vector k here, which is projected on this baseline, and this introduces a phase which is 2 pi over lambda times the distance sine of the angle. So what you can see here is actually that your signal that you received at the ND's antenna is actually phase shifted by this phase that is introduced, and this is a linearly varying phase because here you have this n index. So in other words, this is a unique signal that is phase shifted uniformly along the antenna array, and this, in other words, is a Fourier transform because this is a uniform frequency step, phase step. So now what we end up having is a matrix where we have this time domain information which will give us the range compression, and in this direction here we have the antenna position. So this is your space-time matrix. And what you see now is that it would be natural to try to recover the azimuth information through the Fourier transform because of this property, because along this axis here we have a uniform phase variation. And as we've seen earlier, range compression is a correlation, and correlation is the inverse Fourier transform of the dot product of two Fourier multiplications. So it's natural to consider that range azimuth compression is a 2D Fourier transform, where range resolution is only given by the signal bandwidth, while azimuth resolution is given by the displacement range and the wavelength. And another way of seeing this, it's a very nice demonstration from this website here, which tells us that the 2D Fourier transform of this quantity here of two sine wave is a Dirac function. So if at the end we would like to have a single target at x0, y0, then we must try to find an expression where we separate the x and y quantities. Now, if we go from the signal that we receive at time p and q position, you see here that with respect to the radar cross-section data, we only have the phase information, which is given by the q frequency and the p position of the range to the target. And this quantity here mixes the range and the azimuth. So what we need is to separate these two variables. And what you do here to separate these two variables is you take the Taylor expansion by assuming that the range variation is much bigger, the range to the target is much bigger than the displacement of the antenna. And under this assumption, you can separate the range and the azimuth. And thanks to the separation of the two variables, you end up having these two quantities that are separate. Now we have a range quantity, we have an azimuth quantity. And so what you end up is having a 2D Fourier transform. I'll let you go through the detail of this demonstration, but that's the basics of why you can do a 2D Fourier transform to recover azimuth. So once you've addressed this mathematical analysis, you can take your pattern where you have antenna position and range. And if you take a Fourier transform along this direction, you see here azimuth compression, where you've got the sine of the azimuth over here, you've got the range over here, and you see the various targets that have been compressed along the azimuth. And if you transform the sine of the azimuth into an angular information using this mapping here, you end up with having your various targets at the various azimuth and range, and that's your range azimuth compression. You can do this a bit more fancy than a basic Fourier transform. You can make a full back projection algorithm as using the full expression of the previous slide, and this is what you get. And if you filter properly your back projection, you get the various targets in the azimuth and range that gives you the spatial resolution that we're looking for. So if we do this, well, actually the beauty of this calculation is that there is no degree of freedom, because this range information is only given by the bandwidth of the signal, and the azimuth is only given by the spacing between the steps. And so you have no degree of freedom when you map these reflections over aerial photography. So we see here a few echoes of our noise radar, and if we zoom in, we see now with a lower threshold that indeed the house is generating some echoes. We have a various few other echoes here, and these roofs of the box parking lots here are acting as corner reflectors. So here you have echoes, very strong echoes. So now this proves us that indeed the echo around 48 meters was from the house. Here is the tree, and here are the few corner reflectors from the structure of the roof of these box parking lots. And here are a few echoes from this building here. We can do the same with the Wi-Fi. You see here some, this is only a 0 milliwatt output. I put an attenuator, and using Bastian-Bussel's packet spammer for continuously streaming Wi-Fi information over the full 55 megahertz bandwidth, we see here a few echoes. Again, the house, the various roofs here, and some echoes a few tens of meters away. So this is working very nicely. So this is the basics of synthetic aperture radar. Now, can we go even beyond and use interferometric synthetic aperture radar? Interferometric synthetic aperture radar is based on the idea that your reflection, so far we've only used the magnitude of the reflection, but actually your quantity that we record is an IQ stream, which is a complex quantity. And each one of these targets will reflect an information whose phase is representative of a fine displacement from one image to another. So if we look at this phase information here, we might be able to recover a fine motion of a target. So of course the roof is not going to move. So what we need is to create a reflector whose radar cross-section is about the same as the various targets, the cars here, but which is much easier to move because we want to look at fine motion of the target. So this is a corner reflector, and my colleague Philippe Abbé assembled this for me. So these are 3 plates at 90 degrees, one from another, and we locate this corner reflector here, and we try to analyze the phase of IQ coefficient when this reflector is sending the beam back to the emitter. Now, to do this, you need to have reproducible position of the antenna, and this is achieved by motorizing the displacement. So this is a bit more of a fancy setup. Again, my colleague assembled this for me, where we move the antenna with a rail along known positions every quarter wavelength. Here, using dedicated microcontroller, it could be a Raspberry Pi used for moving the antenna along the rail. This is actually quite a slow setup here. In this experiment, it takes about an hour to make a full 1.4 meter long sweep, but this is the result that is achieved. Here is your house. This is the 2 echoes that we saw earlier on the roof, and this echo here, this guy, is the corner reflector. If you remove a corner reflector, you have a strong loss of reflection. This proves that this is the corner reflector position, and this is the phase when the corner reflector, with reference to the reference image where the reflector was moved by 0 centimeter at the end of the experiment, was moved by 1 centimeter, you see it over here, was moved by 2 centimeter, you see it over here. So you can recover from the phase the fine displacement. If you repeat this experiment many times, you can address how the corner reflector was moved by steps of 1 centimeter, and by analyzing the phase here, you see that indeed the phase is moving over a full wavelength, half wavelength actually, because of the two-way trip. And on the other hand, the roof over the one-day measurement has not moved by more than 4 millimeters. What is this 4 millimeter phase variation? Well, actually a tentative error budget tells us that on the one hand, the local oscillator here is shifting a little bit, and I will not get into the details of the calculation, but if you look here at how the phase noise of the local oscillator, because there is some delay between the transmitter and the received signal due to the target distance, this accounts for about a 0.1 millimeter variation. And the most significant variation is weather conditions. So the temperature has been shifting over the full day of the measurement. It's been raining a little bit, the moisture level has been changing, and if you account for the variation of the optical index, which is well documented in the literature, this is the pressure, this is the water partial pressure, this is the temperature, you have here the variation of the optical index, and that accounts for about 0.6 millimeters if your temperature is varying by 10 degrees, 10 Kelvin, which is about what we see here. And actually the strongest contribution is moisture, and moisture will account for a couple of millimeter variations. So at the end, by adding these various weather condition and local oscillator variation, you end up with about a couple millimeter variation over a full day. So to conclude this presentation, we wanted to show how using software-defined radio, you can make a software SDR-based radar system using various spectrum spreading techniques, whether noise radar or OFDM, by taking the best of each of these frameworks, GNU Radio, Python, Octave. We've extended this analysis to synthetic aperture radar, and at the end, we went into interferometric displacement measurements, showing that there is some variation of the range due to local oscillator fluctuations and weather conditions. You can check the GitHub of this project to get the scripts for processing and acquiring data, and further perspective are to apply this knowledge to satellite radar systems. Europe is giving you freely the Sentinel-1 data sets that you can download on this place, and these are the raw IQ data that you can process using this kind of information. So have fun processing this kind of data, and thank you for your attention.